Section 1.53, the integral of a derivative. Actually, what we're talking about is sort of like an part of the fundamental theorem of calculus. Suppose f is a continuous function on a closed interval ab, and the big F is a function in such a way that it is differentiable and its derivative happen to be exactly the same as f, small f on the interval ab. Then the theorem states is the integral of from a to b of fx dx is actually the big FB minus big FA. Now that is something we're very familiar with from elementary calculus, but now we're going to actually prove it. And the proof is actually very straightforward. We're just going to use the fundamental theorem of calculus to prove it. So first, we know that, so here's the proof. First, we know as given that f prime of x is equal to fx. Okay? And then the fundamental theorem of calculus says that the derivative of this thing right here, from say a to x of f t dt, the derivative of this thing is also fx. And furthermore, we also know that being the derivatives are unique up to a constant, we can define a function, we'll call it g of x. And we'll define g of x as f of x minus this thing right here, a to x f t dt. Now both big F of x is given. This is what we know from the fundamental theorem of calculus. These two things both have the quality such that their derivatives are going to be equal to little f of x. So, which means that g of x, by definition then, because of this definition, g of x, it has to be a constant because the derivatives are unique. So any two functions that have the same derivative, they can only be different by a constant. So then, so remember g is a constant function. And now we're going to do some calculations. What is g of a? Now g of a is equal to f of a, of course, counting from this formula, minus evaluating from a to a is going to give you 0. So g of a is simply f of a. Next, we calculate g of b. What is g of b? That is, of course, equal to f of b minus this thing, the integral from a to x, copying right here, f t dt. Well, however, remember, g of a equal to f of a. Actually, first, we'll say g of b equal to g of a, okay? Because g is a constant function. And then g of a is equal to f of a, which is what we found out just now. So which this thing means that this means exactly this. So we got right here over there. So in other words, what we have, if you rewrite it, then it becomes, put this thing on the other side of the equation, you have ax ft dt equal to fb minus f of a. So this is kind of like a corollary of the fundamental theorem. Is being that we got the fundamental theorem, then the result of any such integration, if you can find the big F, is going to be the fb minus fa. In practice, of course, we can't find a convenient function. We'll just use this and do the math the hard way. Either way, it will give you this result. Now, it is very important when you calculate this to notice that the condition f has to be continuous on the closed interval. As an example, let's, for example, show you a quick situation where, say, if you calculate 0 to pi of secant squared dx, x dx, and what is the answer of that? If you do not care what this is, which you should care, because from 0 to pi, the secant is going to be undefined at pi over 2, because the cosine is 0 there, and then which means the sine, the 1 over 0 is undefined. So So this is function is not continuous from 0 to pi. But if you don't pay attention and you just do some thoughtless manipulation like following that rule, then you go from 0 to pi, and that will give you 0. And that is wrong because this is wrong. And the reason this is wrong is because the integral from 0 to pi of secant squared cannot be 0 because secant squared is a positive function. So there's some stuff there, okay? The area under curve cannot be 0. But this happens because this thing is not continuous. So whenever you have not continuous curves, then this formula might not work.